Let us now talk about fossil fuels and all sorts of fuels and how our society has changed. Look back in 1800. All the way up to 1800 1875, wood was the predominant source of energy in the United States. In a lot of places, wood still is the predominant energy source, right? Then they started coal in huge amounts. Oh my goodness, it went way up. And this was used not only it was used primarily, I'm sorry, for heat. Okay. Then we see the rise of petroleum. This is just oil. Natural gas. This is methane. Oh my, and then here comes nuclear power. And starting in the Great Depression and beyond, they really started building dams and harnessing water power. But today, our major sources of energy are these three, and they are all fossil fuels. What is a fossil fuel? Well, you could say no fuel. There's no fuel like an old fuel. The sun is our oldest and most important fuel source. What we have is it's being utilized as an energy source for photosynthesis. Well, how do I get to fossil fuels from there? Just a second. Endothermic, that means energy is absorbed versus the exothermic, and we can write the energy as a reactant. And you'll notice that's the same thing I got from the from the metabolism of glucose and oxygen to make CO2 and water. They are the same reaction in different directions. Fossil fuels, they've been formed for over millions of years. In fact, the predominant source was formed during the Carbonious, I'm sorry, the Carbonious period about 360 million years ago. And they've been sitting around them for 360 million years, and you saw in the last 150 years, this is when we've started using them. So this is an incredibly new phenomenon for the globe. There are only three of them. They're mostly from the decomposition of plants without any without any air around them or oxygen around. And they are composed primarily of what we call hydrocarbons. Those are molecules containing simply molecules containing carbon and hydrogen. Here are some fuel values. This is how much energy we get out for every gram we burn. And this is for the combustion with O2. Here's wood, gasoline, which is a mixture, coal, that's hard. It goes way down when it's less high quality coal. Methane, again, this is my natural gas. These are my three that are considered fossil fuels that come from fossilized formation of dead plants and a few dinosaurs. Okay. There are a lot more plants than there were dinosaurs, though, so that's the reason why we say plants. Propane, that's another hydrocarbon. Hydrogen, we'll talk about that later. And here's my ethanol. Ethanol is about the same as coal and 50% lower or smaller fuel value than gasoline. It is puts out much less heat when it's burned. Let us look at each one of these, a few snippets of each, and then we'll look at them more closely. Like I say, natural gas, notice how they're all different states of matter. One is a gas. This is CH4, methane, the simplest organic species. It provides 2/3 of the heating of homes and businesses in the U.S. It is a useful source for generating electricity and powering cars and trucks. It burns most cleanly because it's the most pure. All three. And does not have many impurities. The only impurities, I guess, would be other hydrocarbons that sit in there. It has the highest fuel value. Remember the previous page of all three. Coal. Coal is the most abundant, and it has a general formula that's pretty intense. Okay. So that's kind of the general formula. And of course it varies. It's a solid with a lot of impurities. Oh my gosh, this stuff has got everything from lead to mercury. One of the big problems is the sulfur. It makes SO2 when it's burned, and this in turn leads to battery acid, sulfuric acid, with rainwater. When you burn this stuff, like when you're making, this is used a lot for coal, I'm sorry, for electrical power plants. That's its primary use now. It used to be used for heating, but natural gas is much easier to transport, much easier to use, much cleaner. It is, like I say, by far the most abundant. 80% in the U.S. of fossil fuels are coal, 90% globally. It is nasty, nasty stuff. It comes in various grades, from very hard to very soft, black to brown, the levels of carbon versus impurities, and all of it is dangerous to harvest. It is dangerous to mine, dangerous to, well, its recovery from underground deposits is expensive, dirty, dangerous. It is difficult to transport, usually by rail, and it is dirty, nasty stuff to burn. Petroleum oil is composed of hundreds of organic compounds, mostly. And it is the most utilized of all the fossil fuels, as we saw in the previous slide, and it's primarily for transportation. Cars. Expected to remain the dominant energy source, and today tens of millions of barrels a day is utilized, and by 2025 we're talking about 100 million barrels a day. Over 80% of this stuff is used for simply transportation and some heating. It's so wasteful. It's like burning $20 bills. Crude oil contains so many useful sources of organic carbon that could be made into more expensive products. It's so precious to a chemist because this stuff could be a valuable carbon source feedstock for plastics, fabrics, cosmetics, pharmaceuticals, and we're just sending it up into the air. It drives me nuts. Okay, this is how many millions of barrels a day. This is our domestic supply, pretty stable. This is for the U.S. Net imports have gone up. This is the oil embargo. They went down somewhat as we reduced, as we reduced our uses by increasing the fuel efficiency of our cars. And this is a reflection of the fact that we haven't increased our fuel efficiency at all since then. Plus, there are a lot more cars. There are twice as many cars today as back in the early 80s. This is one of our big problems here. Where do we get it from? Well, a lot of places we get it from are not very friendly to the U.S. Right? Well, Saudi Arabia is by far the largest supplier, and that's why you see a lot of interaction between the United States government and the Persian kings. I guess the Saudi Arabian kings, I'm sorry. Today we import 60% is imported. And appreciate that back in the height of the oil crisis, it was only 35%. In 1973, I don't know if you've seen pictures of this, where people lining up to get gasoline, and we are almost double the amount that we're importing now. With 5% of the world's population, we consume 25% of the oil produced. What do we do once we get it in here? We refine it. And this has been a useful source of employment for many chemists. Crude oil is a mixture. Refining is a term we use to mean that we separate the crude oil into different components. And it's just a big old tower. Okay, and here she is, a little bit more detail. Let me take that off so you can read what this says on the side. Of course, it's available in your book as well for more detail. Okay, you stand the crude oil in here, you heat it up, control how much you're heating it. Out the bottom comes the really heavy, nasty crude stuff, waxes, asphalt made into other products. The vapors start traveling. They go up, 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 up. And the point here is it's separated by the individual boiling points of the different components. In general, the bigger the molecule, the higher the boiling point. So boiling points increase as the molar mass increases. That's a big point. Okay. All things being equal, all the rest of there are other factors involved, but in general, boiling points increase as the molar mass of the molecule increases. So who's going to be at the top? Well, you already know that methane's a gas, but you can get some other hydrocarbons from 1 to 4. So this would be methane, ethane, propane, butane. So that's number of carbons that's in the molecule. Down here is where we're going to get gasoline. Gasoline is predominantly a hydrocarbon with 5 to 12 carbon atoms. So gasoline is still a mixture, but it's mostly made up of hydrocarbons that are 5 to 12 carbons in them. Right? And like I said, this is a mix. Okay. This is just like they do with, well, not to belabor the point, but you do this kind of separation a lot. Something that's more viscous, as you might imagine, these kerosene, lubricating oil, they've got much higher molar masses or molecular weights, if you will, and they come off. They need much higher temperatures to keep them as gases. So what do? From 1 barrel of crude oil, we maximize the amount of gasoline. Almost half. And then much of the other is used for fuel oil, jet fuel, heating, boilers, and then a small amount is used for feedstocks that the chemists would like to get hold of. 80%, 90% of each barrel is just stinking burned for no good reason other than the change in volume from going from, for example, changing the volume from going from gasoline to CO2 and water. That pushes the pistons in the internal combustion engine, or simply for heat. Where does your gas dollar go? Well, at this point, this was in 2003, 43% went for crude oil, 30% went for taxes, refining 15%, and retailing 13%. The amount of those 5 to 12 carbon atom chains that make up gasoline is really not enough. We also have to do manipulation of molecules. What we'll do is chemists will crack them, that break larger ones into smaller ones. You'll combine smaller ones into bigger ones. And we can also rearrange the atoms to get more useful properties from these. These are called isomers. They different compounds with the same chemical formulas. The best example that's given of this is our friend octane. Remember when we were doing the thermochemical reactions? We have octane from the 8, and the problem is that pure straight octane is a really lousy fuel. It burns just too fast. It's too easy to burn. So what they will try to do at the refinery is make it into something called isooctane, which tells me it's the same 8 carbons, 18 hydrogens, but they're arranged differently in the molecule. And why do they do this? Because they want to reduce preignition and knocking. They could do this really easily when they could put lead in, but we can't put lead in. This is obviously premature firing. You don't want the gasoline or the fuel to go off simply when you are compressing it. Premature ignition, premature firing, I guess. You get premature firing of the cylinders because this stuff ignites due to just compression. Knocking happens after the spark ignites the fuel, but before the flame has burned all the fuel in the cylinder. The fuel then burns too fast, and the piston receives a single hard slam rather than a strong, smooth push. So this is because it burns too fast. You can sometimes hear it as the engine's turned off too, um, because you'll have residual fumes in there start uh, burning. I guess that's, yeah. You'll find that the fumes will start igniting, and even though the car's turned off, you'll hear this boom, 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 boom. This may just be annoying, but it also uh, can result in severe engine damage. If you look at an octane rating, this is an indication of how well a fuel resists knocking and pre-ignition. The 0 point is heptane, and heptane is a 7-carbon hydrocarbon. So heptane has 7 carbons in it. Isooctane is the top, and he's at 100. This is just a arbitrary um, rating system between 0 and 100. Actual octane is minus 20. Methanol, it's 107. Ethanol is 108. So they're even better than isooctane at resisting pre-ignition and knocking. If you use a 87 octane fuel, the gasoline has the same knocking characteristics as a mixture of 87% isooctane and 13% heptane. This is a branched structure. You can take a look at it in your textbook, and this is just a straight chain of carbons. So this one just looks like this. These are all covalent single bonds. 1, 2, 3, 4, 5, 6, 7, 8. And each of these has hydrogens coming off. Each carbon has to have 4 bonds around him to be happy, to be stable. So you'll notice that he may have different number of hydrogens depending upon where he is in the chain. And hydrogen here. And isooctane is not this straight chain, but has the branching, like carbons appearing like this. And to be honest with you, I cannot remember exactly how it goes off, but there'll be 1, 2, 3, 4, 5, 6, 7, 8, and then I just complete 4 around each guy. And usually, as you can see the mess I made up here, we usually don't even bother writing the hydrogens, we just assume. Okay? What about this MTBE? This is an additive they put into gasoline, again, to make it behave better. It is a molecule with oxygen in it, so it makes it fire more easily. These are additions that were made to enhance the performance after the elimination of the lead. And there is my ethanol. She also has an an oxygen in her that makes it burn differently, better performing fuel. But there's now concern about this material because it very easily gets into water, groundwater. We use these additions, and they're important because that's one of the things that's keeping the refineries going and the price of gasoline up, is figuring out the formulas or the recipes or how much they should put in of these materials depending upon whether it's summer or winter, where you are in the country. You want the gasoline to have different properties. They call them boutique fuels, in fact. And then different states require different amounts of these materials in them, or maximum amounts. Like MTBE, California has banned. So back to the drawing board for that. Reformulated versus oxygenated. The oxygenated have the oxygen in them. And what we like about them is sometimes combustion engines make carbon monoxide, which is a poison, and this will convert it to a compound with more oxygen in it, CO2, which, while not harmful to people, is a greenhouse gas. We will look at that later. The Clean Air Act requires this percentage of oxygen by weight in many cities to reduce this, as well as control some ozone. And he is also a branched, which increases his octane rating. It's harder to burn something when it's branched. All right, reformulated gasolines, RFGs. You're trying to reduce the amount of volatile organic compounds, which are nasty. And these, for example, like benzene is a carcinogen. Hey. You also add them so they evaporate less readily. Not just smelling the stuff, but you want, yeah, I guess that's a big deal, is when you are pumping gasoline, a lot of it's lost, or a significant, I won't say a lot, but a significant amount is vaporized. So ozone's becoming a big problem in urban areas. We want less ozone, less CO2. You increase the amount of reformulation additives during the summertime. A couple other hydrocarbons that are becoming very popular are syngas, or synthesis gas. You take coal, you add steam to it, this purifies it, and then you get a mixture of methane, hydrogen, and carbon monoxide. These then are burned as fuels. Biomass is another, and these are all hydrocarbons. That's carbon plus hydrogen in many different forms, sometimes with oxygen in it, a little bit of oxygen, like in ethanol. So we burn wood, yuck, that has so many different things in it, plus it has a horrible, horrible fuel value, so you got to burn a lot of it to get enough heat. Ethanol, problem with ethanol, and we'll go into it in a second, and garbage. There's so much crap in garbage, excuse me, but we had the trash burning power plant down south of Columbus, and they found that it put out prodigious amounts of dioxin, which is a carcinogen. Biodiesel fuel is on the rise. It's made from natural renewable resources like used vegetable oils, animal fats. They'll use that on the Ohio State campus in many of the buses, and it smells like French fries. You do have to treat it. Of course, you have to clean it. You have to break down the oil from a consumable oil, you know, and it is chemically different than just a petroleum oil. Petroleum oil does not have oxygen in it. Consumable oils do. You have to take glycerin off of it, so it does have to be treated. Ethanol is renewable, but more expensive than gasoline. It takes more energy to produce than gasoline, and it also takes more energy to produce it than you obtain from burning it. Now, the problem too is that you're taking a food away from our storehouses, and this is very far-reaching. You've probably seen the prices going up in your grocery stores. This is all because a lot of this stuff, the corn growers can get a lot more money selling it for ethanol for fuel. Now, the American Chemical Society has asked Congress to take advantage of the current concerns and come up with, for the first time in a long time, a comprehensive and coherent policy which does not depend upon fossil fuels. So where do we go from here? We've got nuclear, batteries, and renewables.